This is David Spears, civil engineering instructor at Texas Tech University, talking about CE 2301 statics. We're talking about position vectors right now. Up till now we've been talking about force vectors, and position vectors are a different kind, but they are still vectors. They have a magnitude, a length, and a direction in space. The format that we're going to use is R. We're going to call most of our position vectors R, and then tip over tail. The tip, where the vector is directed at, divided by over, relative to the tail, where the vector starts at. Position vectors define positions in space, both absolute relative to an origin and relative, a point to a point, one point relative to another in the position in space. So their distance is also, the magnitude is their distance, and the components tell you what direction they are in. So we show here on this diagram 2 points, A and B. Point A is at coordinates X, A, Y, A, and Z, A. Similarly, B is at X, B, Y, B, and Z, B. Just the coordinates of it in this three-dimensional coordinate system. So we say that the vector RA is XA in the I direction, X direction, YA, just the coordinate in the Y in the J direction, and ZA, just the Z coordinate in the K. Similarly, RB is the same way, just using its own coordinates, XB, YB, and ZB. Those are the absolute position vectors relative to the origin. Now we call the position vector RBA, meaning the tip over the tail is the position vector of B relative to position A. So I've shown that in blue here, B relative to A. I just take the coordinates of B and subtract from them the coordinates of point A. So it's XB minus XA. That's the amount in the I direction, or the X direction. Similarly, YB minus YA in the J direction, plus ZB minus ZA. It's tip minus the tail coordinates. That gives me B relative to A. I can reverse that and show A relative to B as RA over B. That's equal to the negative vector of RB over A. Just similarly, just reverse the order of the coordinates, subtracting one from another, subtracting the B coordinates from the A coordinates. I get this format, and like I say, that's A relative to B. They are really just the negatives of each vector, and we can also know from vector addition, RB, this vector RB, is equal to RA plus RB over A. So we can rearrange, subtract RA from both sides, and I get that RBA is equal to RB minus RA. Similarly, RAB, which is the reverse of RBA, is equal to RA minus RB. Okay, one of the big things we want to know from position vectors are the distances. So I can determine the distance from the origin to point A by using trying to figure the scalar magnitude of vector RA. That's really just the square root of the sum of the squares, x squared, y squared, and z squared. Same thing for B. The distance from the origin to the point B is the square root of the sum of the squares of the three components of RB. And then even more useful, or equally useful, is the distance from A to B, between A and B. It's the magnitude of the vector RBA. It's also the magnitude of the vector RAB, because it's the same distance. So I just take the square root of the sum of the squares of the vectors, either RAB or RBA, and I can get the distance. So let's look at those in an example here. I'm given that the coordinates of point A are 3, -4, and 12. Everything's in meters. The coordinates of point B, right here, are 4, 2, and 4. So I can write position vector A, RA, as this. It's really just the coordinates of it. 3i, -4j, plus 12k. Units are meters. RB, this vector here, is just the coordinates of point B. 4i, 2j, 4k. To figure the distance from the origin to point A, I just take the square root of the sum of the squares. 3 squared, 4 squared, and 12 squared. Square root of that's 13 meters. The distance from the origin to point B is square root of the sum of the squares. 4 squared, 2 squared, and 4 squared. That's equal to 6 meters. Now I want to get a position vector from B to A. From A to B. So we call that RB over A, and that is, I subtract the A coordinates from the B coordinates. So the B coordinates are 4 for the X direction, 4 minus 3, 2 minus -4j, 4 minus 12k. Do the math, you get 1i, usually wouldn't show the 1, plus 6j, 2 minus -4, and 4 minus 12 is -8k. Reverse the order of the subtraction, and I can get vector RAB, which is the coordinate of A minus the coordinate of B, so it's 3 minus 4, -4 minus 2 in the J, and 12 minus 4 in the K. So it just looks like the reverse, all the signs are reversed from RBA, -1, minus 6j, plus 8k. Everything's meters. To figure the distance between A and B, it's just the square root of the sum of the squares, which is the same for RBA or RAB. So it's 1 squared, 6 squared, and 8 squared. It's equal to square root of 101, which is equal to just approximately 10.0 meters.